Hey everyone, welcome to your next period of instruction. This period of instruction will be on the Big Bang Theory. There are three primary learning objectives this period and one secondary learning objective. The primary learning objectives are the proper definition and description of what the Big Bang is and what the theory explains, the evidence supporting the theory, the timeline, and the future of our universe. The secondary learning objective is what common misconceptions about the Big Bang are. This is not going to be an all-encompassing class on the theory. This is a basic introduction covering key points because the theory is far more comprehensive than it may at first appear to be. Future periods of instruction will detail more specific aspects. Each of these periods of instruction will have a link to a past video I did. It's a primer on common scientific terminology like theory, hypotheses, and laws, along with other commonly misunderstood terms. If you are unfamiliar with those terms as science uses them, I would suggest watching that before continuing with this. The Big Bang Theory, proposed in 1927 by George Lemaitre, is a cosmological model for the observable universe that details its development from the earliest known periods onto the large-scale changes it has and will go through. I say earliest known periods because we currently do not know for sure what the cause of the Big Bang was, or much of anything from the singularity to the end of the Planck epoch. This is because the laws of physics as we know them and currently understand them break down in that time period. We're only talking about the barest fraction of a second here, though. It is important to note that the Big Bang is not an explosion. It is a rapid expansion of space and energy, not matter. The theory accounts for and explains in detail several phenomena, including Hubble's observations of an expanding universe, the cosmic microwave background radiation, light element abundance, and the large-scale structure of galaxies, superclusters, and other larger stellar phenomena. Measurements of the expansion rate of the universe place the initial expansion at around 13.8 billion years ago. There are several lines of evidence supporting this theory, but we will focus on three of the main ones, starting with Hubble's law. Now, Hubble's law is the observation of two things. First, that objects like galaxies in deep space at distances of 10 megaparsecs, or about 32.6 million light years away or greater, are redshifted, meaning that they are traveling away from us at a sufficient speed that the wavelength of light stretches in a Doppler effect, like hearing a train horn traveling away from you. This shows that they are, in fact, traveling away from us. Second, that the measured Doppler shift is proportional to the distance from the Earth, as in the further away an object is, the greater the Doppler shift. Now, these objects are not speeding up on their own, as they are not propelling themselves. Space itself is the cause of this, because it is expanding. That causes these redshifts by moving these bodies with the fabric of space-time. They are still moving through space, but because space is expanding, and at a very significant rate, I might add, these celestial bodies appear redshifted to us. Knowing this, we can extrapolate back with the known laws of physics, including general relativity, to a more compact universe in the past, colloquially known as the singularity. Next, we have the cosmic microwave background radiation, or CMBR. This is an omnidirectional signal, first discovered by accident in 1964, and is also redshifted in wavelength. This was predicted in 1950 and occurred after a period called recombination, which was the epoch in which neutral hydrogen became stable and the hot, dense plasma allowed photons to freely travel, making the universe transparent in a sense. Study of this phenomena has ruled out a few cosmic inflation models, but is consistent with the theory overall. Finally, we have galactic distribution. Stars and other large celestial bodies, like galaxies, have been aging and changing over time. Distant galaxies, which due to the speed of light are observed as they were in the early universe, look very different from ones closer to us, which can be seen in a much more recent state of development, allowing us to use the known laws of physics to understand, with overlapping developmental stages, how these and other phenomena like superclusters form. The state of these observed bodies tracks with the Big Bang model of cosmology. The timeline we have for the cosmos is divided into several periods of development, encompassing a few stages each, starting with the singularity and the expansion, which can be understood as the start point, or the early hot and dense state of the universe. This marks the birth of our universe and is the point where the laws of physics as we know them start to be useful and actually work without giving us infinity results. This is directly after the end of the Planck epoch, as mentioned earlier, which is a time of an infinitesimal length, less than fractions of a second. This has been calculated to be about 13.8 billion years ago, using calculations of the rate of expansion and fluctuations in the CMBR temperature. Despite the density of energy in early particles at this stage, the universe overcame a recollapse into a black hole due to the rapid expansion of space itself. This was the phase that determined whether matter as we know it or antimatter was going to be prevalent. Matter as we know it won out, with protons and electrons having the charges they do instead of being the opposite in antimatter. Protons, neutrons, and electrons formed from subatomic particles about a second after the initial expansion and formed the first actual matter in the form of hydrogen, helium, and deuterium. A few minutes later, and as space continued to expand, it started to cool down. Over the next hundreds of thousands of years, electrons and nuclei continued to form atoms, which is the source of the CMBR. Through gravitational attraction, clumps of these newly formed atoms condensed into large clouds, stars, and other structures that we see today. Now, this unfortunately brings us to the ultimate future of our universe. It was once thought that the universe expansion would slow down due to gravitational forces and eventually collapse back down in a big crunch. Current data does not support that, though. The universe is not only expanding, but that expansion rate is accelerating. This is commonly attributed to a little-known and largely mysterious phenomenon known as dark matter, which I will cover in more detail in another period of instruction. The implication is this. By all indications, the universe is a closed system, which means that everything will slow down and cool down over time. The continued expansion will separate everything out so much that gravity will not be able to pull things back together, leading to a complete dissipation of matter and energy. A heat death, where there are no longer even elementary particles to work with. This is still a long way off, many billions of years in fact, but it puts a finite limit on how long the universe will last. It's bleak, to be sure, but inevitable all the same. There are a couple of misconceptions to note with Big Bang cosmology. The first of which is the idea that it explains the origin of the universe completely. It does not. From the end of the Planck epoch on back is a complete mystery and is still under investigation, as I mentioned earlier. The next big misconception is that if nothing can move faster than the speed of light, then how can astronomical objects be moving away from us faster than light? The objects in question are moving locally, the same speed that we generally do. The expansion of space carries these objects with it as it expands, which is how they are moving at relativistic speeds. In other words, movement through space is limited by the physics we know, whereas expansion of space is not limited to those constraints in physics. Now, I realize that this ended on a rather bleak note with the whole heat death of the universe and all, but it is unfortunately part of science. The facts don't always lead to a happy conclusion. This will be one of a very few number of videos that could leave you with an existential crisis. That's it for this period of instruction. Your next period of instruction will be on nucleosynthesis, the formation of elements in the interstellar forges that are the hearts and cores of stars.